Hello and welcome. In our series on the environmental impacts of wind turbines, today Hanna Neumann and myself will have a look to the hot discussed topic of the infrasound. So generally, when we are looking on the environmental impact of wind turbines, we discuss topics like shadow of wind turbines to the houses where people are living, of noise emissions, but also of light emissions at night, for example. And as a part of the noise emissions, we also need to discuss this infrasound issue. And both Hanna and me, we are not medical doctors, and we are also not acoustic experts, but definitely it is a topic we need to consider. And so what we did was to look on a lot of studies, on a lot of media reports, how this topic of infrasound is discussed there. And at this point, I also would like to thank a lot our students, Jakob Palm. He really read a lot of studies and helped us with this video a lot. So what we discussed today is now in this first video, we'll have a look on what is sound at all. And then we continue to discuss what is the special thing on infrasound. Then we will also discuss what is the effects of infrasound on humans. And finally, also how this topic of infrasound is used by opponents of wind turbines and wind parks in their arguments. And finally, we have a look how infrasound topic is discussed in media. But first of all, Hanna, what is sound at all? What happens physically that we can hear noise?
Yeah, sound is a mechanical wave progressing in a medium. And in air, it's just variations of pressure and density. Mm-hmm. And the speed of sound is constant and in a medium and for its state, and it is calculated with the wavelength multiplied by the frequency of this mechanical wave. Mm-hmm. So on this graph you can see the sound pressure over time. In the upper left part you can see that if we have a high tone we have many vibrations per second, so we have a high frequency. And on the upper right picture you can see that if we have a low tone we have less vibrations per second, so we have a low frequency.
Okay, and in the lower part of this graph we see that when the amplitude is higher, we consider that noise as more loud, and when it's a lower amplitude, then it's more less loud signal. Hanna, one thing I never really understood when reading all those studies was when we talk about the noise pressure level or noise pressure at all, we cannot read about the physical unit that is pressure. They always give that in decibel. But how can we interpret a value in decibel as a sound pressure level or the noise level of a signal?
Yeah, the sound pressure level is given in decibel. And decibel is the logarithmic ratio scale, so it maps the large value ranges of the sound pressure to small value ranges of the sound pressure level. And the sound pressure level is calculated multiplying 20 with the logarithm of the sound pressure, P, divided by the reference sound pressure, P0, to the basis of 10. And the reference pressure, P0, is 2 times 10 to the power of minus 5. Mm-hmm. And what we have to say that a level difference of 20 decibel corresponds to a 10-fold sound pressure. And we also have to say that the sound pressure and the sound pressure level depends on the distance to the sound source.
Okay.
So on this graph, you can see a comparison of sound pressure level in decibel and sound pressure in Pascal. So on the y-axis, you can see the sound pressure level in decibel, and on the x-axis you can see the sound pressure in Pascal. And when you look on the graph, you can even see that a difference in the sound pressure level of 20 Pascal corresponds to 10-fold sound pressure in Pascal.
Okay, but at least it is really pressure that we measure. So it is when we have this oscillation of the air, then it's this pressure that the air is giving to our ear, for example. But when that is then in the form of a sine wave, a positive, negative, and zero, how do we express? Is it then the amplitude we use for that, or how do we do that?
Yes. On this picture, you can see on the left side the signal of the pressure depending on the time. And in the simplest case, we assume that it is a sine wave. And in case we want to analyze it more, we can use the fast Fourier transform and make a frequency spectrum out of it. So on the right picture, you can see the amplitude of this wave over the frequency of this wave.
Okay, and when we don't have just one frequency, for example, when we have a mixture of a lot of frequency, when we are talking, for example, then we have something like on the next slide here on the top graph. And then we can do this fast Fourier transformation and have then one spectrum with the fundamental tone. And then we can give multiples of them as the harmonics. And then we have this frequency spectrum also with all the amplitudes of that. And how that is the way we can describe more complex noises.
Yes.
And then I need directly to ask my next question. What I also had a problem when reading those studies was that they quite often do not just give decibel levels then, but they talk about a third spectrum or an octave spectrum. Is that not the same, and where's the difference there?
Yes, so the frequency range on the x-axis is usually also divided logarithmically, and you can do this with different resolutions of the frequency. And if you have a very fine resolution, we talk about the narrowband spectrum. Mm-hmm. And in the case we have a medium resolution, we call it a third octave spectrum. And in case of a very rough overview, we have an octave spectrum. And you can also see this on the graph on the right side, where the different spectrums are shown in a schematic. So, and here you can see that the octave step represents a frequency doubling. For example, if we double the frequency from 125 Hertz to 250 Hertz, the range in between is an octave. And the third divides the octave logarithmically in three parts. And the third octave is also used in order to be able to compare measurement results with the human perception threshold. So if we want to find out if a human can hear a certain noise.
Okay. Mm-hmm.
And the level value for third and octave bands is determined by energetic summing of the noise components contained in a band. And here you can see the equation how third octave level is transformed into octave levels. So the levels of the 3/3 are taken into account, and they are logarithmically summed up, and then we reach the octave spectrum.
Okay.
So, and on this graph you can see a measurement of the Landesanstalt für Umwelt Baden-Württemberg. They have carried out measurements of infrasound close to wind turbines. And here you can see in purple the narrowband spectrum. And in red you can see the third octave spectrum. And in green you can see the octave spectrum. And what you can see is that due to the smaller resolution, you cannot see these peaks of the narrowband spectrum in the third octave and in the octave spectrum. But they are contained in the spectrum because the levels are higher.
Okay, thank you very much, Hannah. Now I think we already know a bit the basics about noise, and that is really important when we also then follow the discussions that we have about the infranoise topic. And then in the next videos, we really make the switch from sound to infrasound, and also have a look from where this infrasound then comes from the wind turbines. So thank you very much, and see you in the next video.